Hello everyone, welcome back to Calculus again, and this time we will continue to work on derivatives and the shapes. And first of all, I think this is very simple and important. When the derivative is positive, which simply indicates the function is increasing, derivative is negative, the function is decreasing. And also at a point the derivative is zero, we could have possibly maximum or minimum or neither. And then the real issue is how do we know, okay, if indeed we are having maximum or minimum or neither at a point where derivative is zero. So that is from the second derivative test. And I say it's kind of hard for me to explain, maybe not. Okay, but anyway, it really would be a lot easier if you use an example. So this is the example from the textbook we already did. And if you feel good, still I want you to take a look at that again. Take a look again to see if the discussion makes sense. And then to see if those formal statements make sense. How do we find out the local maximum, local minimum? You really will have to check the derivative all around, derivative to the left, derivative to the right, and then you can decide possibly maximum, minimum, or neither. Okay. And how about to do another example? Actually, this is still the example from the textbook. Find out the local extrema, which really means local maximum, minimum, and for this function if there are any at all. Okay. So usually for this type of problem, you just want to follow the steps, 3 steps. But anyway, a lot of work really. Step 1, clearly we always start from the derivative. And this time, I hope you see these are 2 power functions, right? Even though they may look a little weird, but anyway, they are just power functions. So I calculated derivative in this fashion, and using the power rule, bring down this 1/3 as a coefficient. Certainly the 5 in the front still stays. Then decrease 1/3 by 1. And for the second term, really I use the same rule. Okay, 5/3 as a coefficient, and then decrease the power by 1. 5/3 minus 1, that's 2/3. I think that should be it. And then, the goal is to find out the critical points. So I'm simply setting the derivative equals 0. Because of the negative power, it might be a little harder to consider negative powers directly. So negative power simply means x to the 2/3 in the denominator. And also, I try to combine those 2 like terms. So this is x to the 2/3 in the denominator. 5/3 just stay there. And then let me take a look if I'm getting this part correct. Yeah, actually there are 2 5/3 there, right? So 5/3, 5/3. So they both are taken out as a single coefficient for the entire fraction. X to the negative 2/3, it is x to the 2/3 in the denominator. And also to combine them, those 2 fractions, we need to have the common denominator. So indeed, I multiply x to the 2/3 to the second term too. So I can have x to the 2/3 as a common denominator. And then, well, set this derivative equal to 0. Clearly, this 5/3 cannot be 0. Denominator still cannot be 0. And then the only chance for this derivative equal to 0 is the numerator to be 0. So I figured out there are 2 solutions, 2 possible ways to make the numerator 0, x equals 1 or x equals -1. And then these are the critical points. These are the critical points. Remember, using critical points, we could construct a table. Okay, because when you plot those 2 critical points on a single real number line, they separate the single real number line into 3 parts. The line segment in between, the line segment to the left, and the line segment to the right. And this time, well, when you have a table created in this fashion, then you want to choose an x value for each inequality. There are three inequalities. So x less than -1, you could choose -2, -3, or -4.12, those kind of things. It's really up to you. What I did, just to show the randomness here, okay, I'm simply choosing x as -5. And then I try to put this -5 back into the derivative calculation. Keep in mind, we really only needed to know if derivative is positive or negative. I suppose you do know the denominator for whatever the x value you may have, it's always positive because it's power 2 there. Then for the numerator part, it is x to the power 4/3, -5 to the power 4/3. It's still positive, it is greater than 1. But the 1 minus something greater than 1, this will be negative, right? So indeed, this is what I see. The derivative for any x less than -1 is negative. So the function is decreasing. At the critical point x equals -1, there's nothing to discuss for now yet. Okay, we will look at the situation just in a moment. Then for any x between -1 and 1, I say choose x as 0 would be the easiest choice. If you want, you can do 1/2, 0.37, -4.18, those kind of things. But anyway, make some simple and easy choice. And then I put this 0 back into the derivative calculation, f prime. Actually, I just realized it may not be a good choice. I really should choose something, 0 to the, I cannot, actually I cannot choose x equals 0. Probably I have to choose something, x, because x cannot be 0. Probably I should have chosen something not 0, not like 0, or maybe just do 1/2. Let me do 1/2. Do 0.2, those kind of things. But anyway, I suppose you can verify it easily. The derivative is positive, which means the function is increasing. The function is increasing. You choose 1/2 or -1/2, really the same. Derivative is positive, which means the function is increasing. Okay, x equals 1, that's another critical point. X greater than 1, I'm taking 2. And I'm saying if you want, you can do 5, do 17, any number you want, as long as it's greater than 1. So if I'm taking this as 2, and the derivative tends to be negative, which means the function is decreasing. So think of this very carefully. We have two critical points. At x equals -1 to the left, the function is decreasing. To the right, it is increasing, decreasing, increasing. Roughly, we are having a shape like, I cannot draw anything on the screen, but anyway, I just show the idea. We are having the graph opening upward. Okay, and then for any x greater than 1, little bit to the left of this one, it is, well, it is increasing, and for any x greater than 1, it is decreasing. So roughly in this time, the graph we are having here, for any x less than 1, it's the increasing, and the greater than 1, that's decreasing. So this shape. And then we can figure out, okay, at x equals 1, indeed, we are having maximum. To the left, it is moving up. And then to the right, it is decreasing, moving downward. So x equals 1 must be a maximum, local maximum. Similarly, x equals -1, it must be local minimum. So I also calculated f of -1 and f of +1 here. And then I just realized there is a local minimum at x equals -1. The minimum simply is -4. And also there is a local maximum. See, maximum and the minimum, they possibly could occur at in a given point when the derivative of that point it is 0. Derivative of that point it is 0. Certainly there could be neither, that is the same. But anyway, for the problem we just considered, it is just a case. Derivative it is. At the derivative it is 0. We are having a local maximum here, which is 4. Okay. This is the critical point. -1 critical point for, we already figured out when it is one critical point for it is for the local maximum, the other it is for the local minimum. Basically, that's all about the first derivative test. And also in this section, basically, I think that's all I have for the first derivative test. But anyway, I still want to cover a little bit about second derivative test, the so-called concavity or the inflection points. Okay, and you look at this part of the graph. The graph, we said it is increasing and opens upward, right? And then if you also track the tangent line closely, you can see the tangent line is getting steeper and steeper, goes up faster, which means the derivative itself is increasing. The derivative itself is increasing. So in this case, we call the graph concave up, as shown here, opening upward. This part B, the graph, it's showing the concavity, concave down. Actually, both are increasing functions. Now we can identify one as opening upward, the other as opening downward. Okay. And this is the increasing function. And the two lower graphs, they are the cases for the decreasing function. But anyway, in terms of concavity for decreasing functions, it could open upward or downward. And also for the test of concavity, basically, this is all I need you to remember. There is also the second order derivative test, but anyway, for our class purpose, simply it is not required. Okay. The test of concavity, the only thing you need to remember here is if the second order derivative it is positive, which really means the graph opens upward, the function is concave up. If the second order derivative is negative, which means the function is concave down. Okay. So this is a summary of the discussion about the shapes and the derivatives. And also, don't forget, the reason we consider shapes and the derivatives because they do have a lot of real-world applications, and because they can tell maximum and minimum, right? Like the other examples we did. So some basic conclusion you want to remember about the shapes of the graphs, shapes and the derivatives. First order, second order. And first order derivative positive, which means the function is increasing, and the graph of second order derivative positive, the graph is opening upward. And first order derivative positive, the function is increasing. Second order positive derivative is negative, which means the function is decreasing. Similarly, we may have a decreasing function opening upward and the decreasing function opening downward. These conclusions, they are just from the derivative tests. And thank you for watching. See you next time.